Now let's study section 1.7, Inductance. 1.7.1, Physics of Inductors. A coil with an iron core will have a considerable leakage flux. Flux can be increased and the leakage can be reduced by wrapping the coil around a ferromagnetic material that provides a lower reluctance path. The flux will be much higher using the core A rather than the rod B, as we can see from the photograph. The flux in the photo A is much higher using the coil than the rod B. Assume that all of the flux stays within the low reluctance pathway provided by the core. Therefore, phi is equal to epsilon divided by r. That is equal to N multiply I divided by R. R represents reluctance. From Faraday's law, change in magnetic flux creates a voltage across the coil. Therefore, the voltage E is also called electromotive force is equal to N multiply d phi divided by dt. Therefore, E is equal to N multiply dt multiply the N multiply I divided by R divided by dt. Therefore, it's equal to N squared divided R multiply di dt. So the electromotive force is equal to L multiply di divided dt. Therefore, L inductance is introduced as N squared divided by R. N represents the number of turns. R represents the reflex. A distinction has been made between E, the EMF voltage introduced across the coil, and V, the voltage that may have applied to the circuit to cause the flux in the first place. The V represents the voltage source that creates current produced in the coil, and the current in the coil will create the flux in the I, and the flux in the I will generate the electromotive force. If there is no loss in connecting wires between the source voltage and the coil, which means this wire has zero resistance, therefore the E is equal to V. So the voltage, since V is equal to electromotive voltage E, so voltage is equal to L multiply di divided dt. Section 1.7.2, Circuit relationships for inductors. From the defining relationship between voltage and current for an inductor, when current is not changing with time, the voltage across the inductor is zero. Therefore, if the voltage source is a DC direct current, therefore the inductor looks like the same as a short circuit. So the inductor has zero resistance. When inductors are wired in series, the same current flows through each one. The voltage drop across the pair is the same will be equal to L1 multiply di divided dt plus L2 multiply di dt. So when two inductors are wired in series, the voltage series is equal to L series multiplied di dt. So the L series is therefore equal to L1 plus L2, which is equivalent of inductance of the two series inductors. When two conductors are in parallel, which means they have the current are different, but they have the same voltage. Similar to resistance, the L parallel is equal to L1 multiplied L2 divided by L1 plus L2. The total current flowing the sum of the currents. So the I parallel is equal to I1 plus I2. Since the voltage are the same across each inductor, therefore the integral, we can use the integral to get the L in parallel inverse. The voltage integral over time will be equal to L1 inverse multiply the voltage integral plus L2 inverse multiply the voltage interval. So the L parallel will be equal to L1 plus L multiply L2 divided by the sum of L1 plus L2. Just as capacitors store energy in their electric fields, the inductors also store energy in their magnetic fields. Since energy W is the integral of the power P, the equation for energy stored can be expressed as WL, which is the energy stored in the magnetic field, is equal to the integral of P over time. Since P is equal to V multiply I, therefore the WL is equal to the integral of VI over time. And since the voltage is equal to L multiplied di dt, so the energy stored in the magnetic field is equal to L multiply the integral of I over I. Therefore, the energy stored in inductor is equal to 1/2 L multiply I squared. The power dissipated in an inductor is therefore equal to dW over dt, since power is the change rate of the energy. So, since W is equal to 1/2 multiply L multiply I squared, therefore the power P is equal to L multiply I divided by di dt. This means the current through an inductor cannot be changed instantaneously. Let's see this example. When we have a simple RL circuit with a switch, which means here is a voltage source, and there is a resistance and also connected with inductance. And we set up a measurement to measure the voltage over the inductance. Originally, the switch is open, so there's no current flow. across the inductance. When the switch is closed, the voltage rise due to the battery must equal to the voltage drop across the resistance plus the voltage across the inductance. So the VB is equal to V multiply R, which is the voltage drop over the resistance, plus L multiply di dt, which is the voltage over the inductance. So subject to initial condition, when I is equal to 0, when t is equal to 0, therefore the current is equal to 0. So I, we calculate, can be equal to VB divided by R multiply this 1 minus e, the exponential of minus R divided by L multiply t. So which means at the t equal to 0, the E0 is equal to 1. At that time, I is equal to 0. And one time increase, the E start minus L R divided by L multiply T continue to decrease. And this one is 1 minus this one continue to decrease. Therefore, I will continue to increase until t reaches infinite to the value as a VBVR, as we can see from the photograph. So at 0 point, when the switch is closed, originally the current is 0. And as time increases, the voltage over the inductance continue to rise until it reaches to the steady state, which is the VB divided by R. And at the time capital T, when we suddenly open up the switch, the current quickly drops to 0. As the current changes, the di divided by dt will be significantly increased. The di divided by dt will be much larger than the voltage provided by the battery. So that will create a spike of the voltage. So suddenly the voltage as t equal to capital T, the voltage will go to the negative direction and get a very large value, and then gradually to decrease and quickly decrease to 0, because at that time the current will reach to 0. That's finished section 1.7.